And now we move on to triple integrals. So a triple integral is just like a double integral, except guess what? It's got one more integral. So over a box, and so when I say box, I mean specifically a rectangular solid with boundaries that are formed by sides that are planes parallel to the coordinate axes. So if we have the axes like this, then I'm talking about some region that looks like this, floating in space, maybe out in front or sitting on the plane or whatever. But all of the edges of that box are parallel to some coordinate axis. So if we call this box B, then we write the triple integral over B of some function with respect to the volume element, now that we're in 3D. And then this would be, depending on the bounds for the particular sides of the box, the integral from A to B, C to D, and then let's do G to H, because E is an exponential function and F is a function, generic function, our integrand. And then this would be, you know, dz, dy, dx, or some other permutation thereof. Okay, and so Fubini's theorem applies in the triple integral case as well, and it says that we can interchange this to be anything else. So maybe GH, A, B, C, D, and then GH corresponded to DZ. So now we've got dy, dx, dz. So that's good old Fubini. Fubini. Now, the thing to notice is that before, we were just looking at dx, dy, and there's only two possibilities for that, right? So in 2D, you have dx, dy, or dy, dx. So two possibilities. How many possible ways are there to do it when we now have a dz in there? Well, in 3D, you get to first, so we're going to have like three of them going in order, right? So you get to pick your first one, and so there's three possibilities for the first one. So let's say we choose like dz. And then for the next one, there's going to be two possibilities remaining. And so maybe we choose like dx. And then for the last one, well, there's only one possibility remaining for the last one because it's whatever's left, right? So in this case, this would have to be dy. There's nothing else it can be. And so this equation, so we have 3 times 2 times 1. So that's 3 factorial, more commonly known as 6. So we have 6 possible orders of integration, and it'll be up to you to figure out what's the best one for a given problem. Hooray! Sounds like fun, huh? Don't worry, it's not so bad once you get the hang of it. We have a bunch of other things that are going to come along too. The first one, I guess, is to say, what if we are not over a box? Well, then we're still going to want to be able to set things up nicely. Perhaps let's suppose there's a rectangular footprint. So by footprint, I mean if we project to one of the coordinate planes. So the easiest idea is to say, well, what if we just like looked down onto the XY plane and we saw that our region has a rectangular footprint like this. So maybe our actual, let's see if I can draw something cool here. So there's our footprint, this shape that we've got down here in the XY plane. So what does this look like? Well, then this is going to be A, B, C, D, but now we're going between two functions. So we've got the lower function, let's call it g of xy. So this one, it's actually, yeah, here, so let me just do it in purple, g of xy. And g of xy is going to be this guy on the bottom, this surface. And then we'll have, I'm messing up all my stuff here. Not f, we want it to be h of xy, and that'll be this part up here, giving the upper surface, right? And then we've got our function f dz, dy, dx, say. Okay, so now look what happens if we have perchance that the integrand is equal to 1. If the integrand is equal to 1, then this becomes a, b, c, d, and then we integrate 1 to get z evaluated from g up to h, so we have h of xy minus g of xy dy dx. Okay, now this looks exactly like what we saw before. So if I had asked you a section or so back again to find the volume of this region up here, we'll call this region E. This textbook likes to use E for three-dimensional regions. If I asked you to find the volume, you probably would have just immediately set it up as a double integral over this rectangle right here of the top surface minus the bottom surface, just by analogy with what you know from single variable calculus, right? That's how you find the area between two curves. If you've got, here's G and here's F, then you find the area between these two curves on AB by just integrating F minus G from over the interval A to B. Right? Lessons from single variable calculus. Okay, so the same kind of thing is happening here. And so now you can see there's some utility in working out what's going on with a three-dimensional integral where the upper and lower boundaries are given by functions, or where the left and right boundaries or the front and back boundaries are given by functions. And if we remove the requirement that that function be equal to 1, the integrand there, well, then first off, I should probably move this because that's no longer going to be equal to it. But now maybe F represents the density of this object, and now we can find out something that we couldn't do with just double integrals. So just as before, we have that the total mass is going to be the triple integral of the density with respect to volume. Just like before, we had the total mass of a thin sheet was going to be the double integral over the region of the density times area. And then if you want to include the thickness of the sheet, then that would be some constant that you tack in there as well. Okay, same basic idea. Okay, so we're going to need to look at the most fully general type of region. And I guess let's say that E stands for elementary region. So an elementary region is going to be one where we can set up the integral of f dv over the region E in terms of, and then on the outermost integral, we can only have constants. On the next one, we can have some function of one variable. And then on the innermost one, we can have functions of two variables. And then we've got some integrand presumably that could depend on all three, and then dz, dy, dx. And so now we set the integral up properly if this variable here does not appear. And if this variable here only is allowed to appear here. And then finally, the last one, it can appear anywhere up front. Anywhere except in the very front, and the most outer. Okay. Yeah, and so the book talks about a region as being type 1, type 2, or type 3 elementary based on what variables are involved in the innermost integral. I don't care about that terminology at all, and I won't really use it. I find it's just like one more thing to memorize that we don't really need. But it's important to know that you can set up the integral in different orders and in and evaluate them in different orders. The last analogy I want to make with lower dimensional integrals is that if we are looking at the average value of some function f, then for one dimension it looks like 1 over the length of the interval times the integral from a to b of f dx. If we are looking at a two-dimensional case, then it's going to be 1 over the area of our region times the two-dimensional integral over that region of f with respect to area. And then in our three-dimensional situation, the average value of a function would be 1 over the volume of that region times the triple integral over the region of f with respect to volume. So they're all completely analogous. And if you want, you can even go back and write the one-dimensional one as the integral over the interval from a to b, and I won't tell anyone.